Thank you very much. So yeah, good morning or good afternoon, depending about where you are in the where you are in the world. Yeah, so my name's Nick. I am from Edinburgh, and I appreciate there might be a wide range of sort of experiences here on the call. So I'm going to sort of explain why, and then some of the compiler background, and sort of show why we do this and how we put this together. And I'd suggest just make it easy for me. I'll talk about 40 minutes odd, and then maybe we take some questions at the end, just to avoid me swapping between windows, if that's okay. I mean, the motivation here, the elephant in the room is why Fortran, and a lot of people ask that question, but it's actually still extremely popular in scientific computing. About 65% of the workloads on our supercomputer, the UK national supercomputer we house and manage, this is a picture of it on the top right being installed, are written in Fortran. And it really is the powerhouse behind lots and lots of things. I've got some examples on the bottom, whether it's sort of jet engines and being able to model a gas turbine, whether it's being able to understand the wake vortices off wind turbines for their placement, or even on the far right, the interaction between oil and water molecules for lubrication and whatnot. It's just ubiquitous. And what I hear quite a lot of, and I'm not sure how true it is actually right down at the bottom of even machine learning stacks, there's a lot of Fortran powering it, things like the underlying libraries behind the scenes. I'm not sure how much of that's Fortran, how much is C++, but really the point I'm making here is there's a lot of codes that have a big impact on our everyday lives that are lots and lots of lines in this programming language. And the developers, the people who write and maintain these, are scientists and engineers. They don't want to be doing lots of work porting them to new architectures. Instead, they just want to use them and exploit them to get their end science or engineering done. And in HPC, there's a big shift to GPUs, and it's really been going on a decade, maybe slightly more. And we've really accepted that in order to get that next level of performance, we have to use graphic processor accelerators. And if you look at the top 10 most powerful machines in the world, all but one of these have GPU accelerators in them. 4 with AMD, 4 with NVIDIA, 1 Intel. And the only CPU-only machine is Fugaku, which is ARM A64 FX. And this picture at the bottom is maybe a slightly traditional view of how we couple GPUs with CPUs in HPC, where there's 2 separate memory spaces, there's a communication layer technology between them, and the programmer thinking about moving memory and data from one to the other, and then reworking their workloads to suit the GPU. And even though nowadays this has changed, actually the memory is becoming more unified, and so that does ease one part of it, people are still having to think about changing their workloads to suit this GPU way of computing. And this is a huge amount of effort for the community. And even though this has been going on for quite a long time, there's still lots and lots of codes that need to be ported over, and a massive lack of expertise more generally, and money in terms of supporting this. And there's a whole bunch of technologies people are using for this. And what I'm going to talk about a bit later on specifically is OpenMP, which is actually quite nice because as the community for many years, we've used OpenMP for threaded programming. And then about 5-6 years ago, they added in this idea, these extensions for offloading onto accelerators, GPUs, or potentially others, using that approach. And again, I'll show you some of this and in context of RISC-V accelerators a bit later on. Now, something I talked about a few times before is, why specifically RISC-V for HPC? And a major reason here is the choice that is provided by the flexibility of RISC-V. And there's different ways of interpreting this. Certainly some centers, Barcelona is a prime example, really going in and getting involved in the development and the production of the CPUs themselves and the accelerators themselves, and doing what we call co-design to get these things suited to the workloads. I think a lot of the rest of us really users and benefactors of what vendors are producing, but still vendors have the choice and the flexibility to develop technological solutions that solve our problems, potentially much more easily than with other choices. And there's quite a lot happening here. I mean, we've seen new CPUs coming out, 64 core CPU at the top right here. That's a couple of years old, but there are announcements for things coming out next year. So we'll keep our fingers crossed here. NVIDIA announced that they are bringing CUDA over to RISC-V, and we're going to be having support for that on the platform. So it's really a quite exciting time, especially seeing what hardware is going to be available on the CPU side. But of course, the big downside, the big challenge here when we're talking about RISC-V CPUs in the HPC center is you've got to change everything. You've got to change the motherboard. You've got to change the software ecosystem. It's a big ask and a big jump. So I think personally, where we are going to far more see this starting to come in the near term is RISC-V based accelerators. And these are already starting to work their way into HPC centers. For instance, Tenstorrent are doing a fabulous job in terms of getting their accelerators out there, whether it be the black hole. We've got some of them actually in our HPC data center as we speak. They're galaxies, which are scaled up versions. Again, lots of people are buying these. But there's a whole bunch of other accelerators as well that are out there. And it really depends accelerator on accelerator. So things like the Tenstorrent accelerator, designed primarily for AI and machine learning, but actually, for scientific computing, can we use it? Can we exploit it? And often the answer is yes, we've got the raw power potentially in the hardware, but maybe the software stack hasn't been designed for that. So maybe there's a bit more of a leap to leveraging that. And again, it's something I'll come back to a bit later on. But also nice illustrations of the flexibility here. For instance, bottom in the middle, this is the Thunderbird by Inspire Semi. That's actually a physical chip I took a photo of at the North America Summit just last month. And they are designing this with HPC first, really trying to address the challenge of the software programmability. So trying to enable this to be programmed first and foremost using technologies HPC is familiar with, and much more as a sort of a CPU viewed accelerator, but just lots and lots and lots of these CPUs. But again, of course, the question is, well, how do we get data on there? How do we decompose our workloads? How do we, limit any overheads that are specific to that architecture? And, bottom right, this thing by CaligoTech, really interesting. This is an accelerator for posits. It's an alternative number representation to floating point, something HPC has been quite interested in, that alternative numeric representation for quite a few years. But what's really nice is the flexibility by RISC-V. They've been able to actually put this together and put this into our hands. And if you're keyed up with the latest developments in RISC-V, you might think it's strange that I've got the Esperanto chip on the bottom left, because very unfortunately over the summer Esperanto closed their doors. But what's really exciting is the AI Foundry have bought the IP and actually have released the software stack open source, and hopefully they're going to continue to some extent that product line into the future. So we are seeing a whole bunch of variety here and different accelerators coming online. And the big benefit is I can just pop them into an existing system and keep a lot of my existing infrastructure and things as they are. And just very briefly, I'll go through this very quickly. The Tenstorrent wormhole, we've had a few successes, and the other people in the HPC community. I suppose the key point I'm making here is one of the benefits of this technology is we're getting the energy efficiency. So we might be able to get reasonable performance. Certainly in terms of the cost level here, it's actually really impressive compared with CPUs and GPUs, but probably more importantly, drawing topically a lot less power or energy to solution. And this is becoming increasingly important in HPC when we're thinking about how to power our HPC systems and also sort of the sustainability piece. There's more focus placed upon these as well. So again, it's not all just about performance, even though that's important. There are these other dimensions that the specialization can potentially help get us to. And I think personally, openness is the key here. And openness really, in many ways, arguably, is promoted at the foundational level by RISC-V, because RISC-V being an open standard, well, already the vendor is leveraging this open thing. And so I suppose it reduces one blocker to them opening things wholesale. And this is important, I think, because the likes of NVIDIA, AMD, they invest huge amounts of money in their software stack. And it's just phenomenal what they're putting in here, developing things like the Fortran compilers, OpenMP I've talked about, all the libraries to support their software, their hardware system. And how on earth can we ever match that? And I think the answer to that is we probably can't. But actually, in the HPC community, is there a way we can pool our resources here? Quite a few of these accelerator companies, they're maybe not primarily focused on scientific computing workloads. Maybe it's more AI and machine learning, but actually bringing them over there to scientific computing. Are there things as the community we can do just to make that much easier, bridge that gap, if you like, between what they've done to support AI and machine learning and these more general purpose scientific computing workloads? And of course, and again, I'll come on to this a little bit later on, when we're thinking about sort of writing compilers and stuff for these architectures, openness is really important. Being able to get deep down into the architecture, understand what it's doing, and being able to drive it. And just a bit of a side note, Tenstorrent, for instance, have really embraced this. They've released loads of information about their architecture up on their GitHub, but also their entire software stack is open source as well. And we did a bit of an exploration here a few months ago, developing a Python simulator just based upon what they'd released publicly to be able to execute binaries that come from their software stack via our simulator rather than actually on their hardware. And it was really, two purposes to this. Firstly, to check that what they were promising us in terms of the openness was the case. We thought it'd be fascinating. Can we just take what they've released in the wild and actually recreate their architecture virtually from this? But also, as I say, when we're developing sort of the compiler tooling and thinking about the performance and how we drive that, to be able to delve in and really see the instructions that are being issued and why they're being issued, and to be able to get maybe much more detailed feedback than we would get on the architecture itself, because they haven't released an easy to use wholesale simulator as such. And it's not just Tenstorrent that have committed to openness. As I mentioned before, AI Foundry, that have the Esperanto IP, they've released on GitHub the software stack and the simulator for this as well. So again, really exciting to see some of these vendors sort of pushing that out there. Now, what I want to do is context shift away from RISC-V, accelerators and HPC, and talk briefly about the compiler side of things. Because again, as I say, I appreciate on viewing the presentation, there'll be a variety of expertise as an interest here. And when I was putting this presentation together, I was actually reminded that my first connection to the RISC-V community was actually talking about compilers back in 2021 on one of the developer sessions. And at the time, I was talking about a Python implementation we'd done that we brought over to RISC-V CPUs. It was sort of this tiny implementation, and the idea was for these tiny sort of microarchitecture type things. And what I thought was interesting, especially within the context that I'm going to talk about with MLIR, is even though at that point I'd not really got in my own mind this appreciation or registering of MLIR too much, this idea on the bottom left of sort of this common ecosystem layer and how we needed this to be able to drive these architectures from a whole bunch of different front ends and front end languages. And often the front end is maybe not that interesting if you can reach a sort of standard interface level. And actually what's more interesting is sort of what's then in the middle and towards the back end, and what you can share here. And this really didn't go very far talking about here, because of the Python side of things, I suppose, but also because there was a much better compiler technology in and of MLIR I'll talk about. But as I say, I thought interesting that for me personally, I was already starting to think about this, even though not explicitly, because what I was trying to explore is going from the software world down to the hardware world and close this gap as effectively as possible, ideally across a whole bunch of different technologies, to make this as convenient and as easy as possible. So we can just bring on a new accelerator, a new RISC-V accelerator, and actually the minimal amount of work is needed so it can be used and leveraged by one of these front ends. And maybe they've done a whole bunch of work on their AI stack, for instance. Well, actually, to make it as easy as possible for that to be connected with more general purpose workloads. And in terms of these front ends, there's quite a few here. I mean, Flang is what we're currently focused on. But actually what we see in HPC is a whole bunch of domain-specific languages, things like Cyclone used by the Met Office embedded in Fortran, and some of these other ones as well embedded in things like Python. But it's the same sort of challenge. There's a big gap between that front end and often the mathematical representation and the actual hardware. And actually, we don't want to reinvent the wheel time and time again. And this is really what I'm saying here. When we started in 2021 with a few other people across the UK, really trying to address this problem of siloing, actually from a starting point in domain-specific languages. So we took a few domain-specific languages. There's two of them here, and we actually said, look, it's pretty worrying that if you peel back the sort of the top level here, these things share no compiler infrastructure whatsoever, but actually are doing a lot of the similar activities. So there's a huge amount of duplication of effort here, and there's a huge amount that could be shared between them. And really, it goes back to my point before in terms of actually, if we step back in the HPC ecosystem, what can we share easily across all these different RISC-V vendors? And so, what we were saying at the time and what we were thinking for these different DSLs is actually MLIR is the solution we want here. And the best way I tend to explain this is the classical way of viewing this is something like what LLVM used to do, which is we had all these LLVM front ends and they would go down to LLVM's intermediate representation. But this in and of itself is quite low down sort of to the architecture. So again, there's a lot of duplication between these different front ends. So then when TensorFlow was developed by Google had this idea of, okay, let's abstract this and have this different hierarchy of intermediate representations through different dialects. And dialects can be mixed together and we can have transformations between them. But really, the idea is if I'm targeting, let's say, a GPU with TensorFlow, and I'm also doing it with, Flang or PyLir, which is Python, and probably quite a bit of what I want to do is the same. It's just stuff really quite high up in the stack that might be a bit different. So the unique things, let me separate it out, and then the shared things I can put in this shared compiler ecosystem. And in 2019, Google released this open source and merged it into LLVM. It's become phenomenally popular ever since then. And so just to give you if you're not familiar with this, a bit of a sort of flesh on the bones, if you like, this is an illustration of some of the intermediate representation. This is from TensorFlow, and it's all textual, follows what we call SSA form. Basically, it's an operation, takes some inputs, produces an output, but that is sort of quite high up in the stack. And then this then gets lowered to another representation here, what's called the affine dialect for doing loops. And you can also see the addition. This might be part of the arithmetic dialect. And then we might lower it further to, for instance, the GPU dialect to target GPUs. And then we might even go further for AMD or NVIDIA GPUs. But really the point is, if you want to plug in new architectures, well, you probably just need to change this bit down here you don't need to change these higher up things up here, and you're avoiding that duplication potentially. So to, again, give you an example of what we were doing, bringing this more into the HPC space, we were initially saying, well, actually, we want to focus on stencils, and we'll develop stencil dialect, and then do lots of optimizations on these stencils, and then bring that down into some intermediate dialects, and then bring it down a whole bunch of different routes for different architectures. So for GPUs, for threaded programming, vectorization, distributed memory, etc., etc. And this is all good. MLIR in and of itself is really nice, but it's also very complicated. And so this makes a lot of sense for a production compiler. But as part of this, we realized when we wanted to iterate quickly and we wanted to experiment with these different things, but also just to integrate it with some of these DSLs, it was quite a big ask. And so we developed this thing called xDSL. And the idea of this is it's a Python implementation of MLIR concepts. So it goes a lot further than sort of bindings for MLIR, because it exists sort of completely independently of MLIR, but it's entirely compatible with MLIR. So you can move between the different ecosystems utterly trivially, but because we are in Python world, it just makes it really, really quick to go from one to the other. And we've had a whole load of downloads on PyPy, and quite a few people sort of using this, but specifically for this this fast prototyping and an exploration. And just to illustrate on the top left, this is some of the Python illustration of a rewrite rules for transformation. And again, what's super nice, and it's the point at the bottom, is you're not having to recompile every time. You do a bit of hacking, you run it quickly, doesn't work, you might shove some print statements in or whatnot. So it really just speeds up this iterative approach often to doing this. Really then the idea being, well, let me make all my mistakes here, and then I'll maybe bake it into MLIR once I've done that, and I get it right in C++ that the first time when I do that for real and in anger. And this is just what I've said in terms of this idea of this sidekick to MLIR. So we've got lots and lots of transformations in xDSL in and of itself, but at any point, if we want, we can just dump into MLIR, run a transformation, jump back out. So we have this complete compatibility between the different ecosystems as well. And actually, the MPI dialect that's in MLIR, well, this started out in xDSL. So we did all the prototyping, and then we brought that through and took that into MLIR from that. So the start of this, if you like, the first step here was taking this idea of a stencil from these different domain-specific languages and bringing it through with these different optimizations for both CPUs and GPUs, running on things like the RISC-V SG2042, and running, pretty transparently on this, leveraging existing parts of the ecosystem. But really the idea being initially to do lots of optimization around the stencils that could then be shared by other things that I'll talk about a bit later on. And then some optimizations around other bits and pieces too. And that was fine. Stencils are good in and of themselves, but obviously there is a certain limit there. And what we then thought, well, actually, a lot of the integration we've done with Fortran here for the Cyclone DSL, actually we can generalize that, because we're already having to go in and pick this off and play around with it. So our next step was to say, well, what Flang does, the new Flang, is this leverages MLIR, but it's a bit strange, the design decision they've taken, because primarily they have their higher level Fortran intermediate representation that they mix with their Fortran intermediate representation. They lower this to their Fortran intermediate representation with some of the core dialects as well, with like arithmetic, OpenMP and stuff like that, and then feed it into LLVM IR directly. And we thought, well, actually, it will give us a lot more flexibility if we go down a slightly different route. If we, still have this initial bit from Flang, but then transform this into the core MLIR dialects. So things like memref, things like a fine, SCF if we want it, all the other things that are part of what's called the MLIR ops tool. And then because you exist within this core MLIR ecosystem, well, our theory was we actually get access to lots and lots of new potential optimizations and transformations, which Flang, sort of sitting a little bit tangentially to, doesn't necessarily always have, or some of them have to be reinvented. But also fundamentally, potentially it gives us a bit more flexibility when we target some of these novel architectures. And I mean, very briefly, this works. I mean, this was results from last year on sort of a CPU, actually an x86 CPU, but also with OpenMP, some of the intrinsics that are driven with the linear algebra dialect, and then also with a GPU as well. But really, our purpose here and our objective was, as I say, to explore whether this sort of alternative route would be beneficial compared with Flang, actually whether it would close the gap with the Cray compiler, which for Fortran is pretty much of a gold standard, and we don't have on RISC-V, but also some of the additional opportunities that it gives us, things like potentially being able to more easily target GPUs and going via the linear algebra dialect for these intrinsics, again, maybe gives us opportunities in terms of optimization and threading things and whatnot for that. So I've talked a lot about sort of the compilers and talked about the RISC-V, and now what I want to do is bring them together, because with the Tenstorrent, what we're very interested in is using this as a bit of an example to drive Fortran flows for RISC-V accelerators. Really, the Tenstorrent architecture being the first step. And I need to be a little bit careful here when I say Fortran. I mean, Fortran is useful for HPC. We're not completely sort of limited or linked with Fortran. Actually, it's the abstractions that are far more interesting to us. So anything that can get in the front door of these core dialects and how we will understand and work with these core dialects, then actually we want to be able to take through it and drive onto these accelerators. And the first thing we did here was this sort of illustration down at the bottom, and we developed sort of two sort of flows, if you like. The first thing that we developed in terms of the flow was our own set of dialects for the Tenstorrent API, the Metallium API. So things like for the compute side, for the data movement side, for the host as well. And then simply a printer that dumps out C++ code with the actual API calls in eventually, and then we just feed it through the tool chain. But at the same time, Tenstorrent have been spending a lot of work developing their own MLIR ecosystem, their own fork of MLIR for that accelerator, and we've also done integration with that. And actually, that was pretty trivial based upon the dialects we've already written, because it's just one route or the other route. And there's pros and cons of both approaches. The pro of our approach is you don't need Tenstorrent MLIR installed, which is quite big and does have quite a few dependencies to build. But of course, the benefit of their approach is they do a whole bunch of optimizations that, again, thinking about this reuse from the AI and machine learning space that have driven a lot of that, is nice to be able to take advantage of and exploit. But what we can also do is maybe go a slightly different route in some ways. And what I mean by that is sometimes, again, going back to what I was talking about in terms of the simulator, it's quite interesting to see the actual assembly calls that are issued to their co-processor, which does all the work for their different Metal API calls. And sometimes you think, well, actually, okay, that probably makes sense for workloads over there, but I don't need it for workloads over here. So again, sort of being owners of our own destiny, so to speak, well, we can embed these sort of different intrinsics, for want of a better word, these different assembly calls here, just through additional operations in our dialects, and then just dump them out. So actually, we again have that specialization quite far down in the stack. And I'm not sure, I mean, because it's changing all the time, so it might be possible now, but I'm not sure if that's possible with their MLIR routes And I say, hence, it just gives us this flexibility. Now, the first thing we did here was to explore Fortran intrinsics on the actual architecture itself. And this is quite easy because Fortran intrinsics are a very constrained problem. These are built-in function calls like a sum or a transposition or a matrix multiplication. And what we'd already done is we'd already lowered these down to the linear algebra dialect. So then what makes it really, really easy is, okay, I've got that lowering already. Let me just connect the linear algebra dialect to my Tenstorrent dialects. And I've been a little bit naughty here. Actually, the image I've got at the bottom left, if you're eagle-eyed, you'll see I don't mention Tenstorrent there. I actually mention AMD AI engines because we did these two pieces of work at exactly the same time. And really the idea was, again, that sharing. We're targeting one architecture, we're targeting the other. Actually, for a lot of that stack, it didn't make a huge amount of difference. We're able to do a lot of reuse here. The one big difference that we did have between these different approaches is for AMD's AI engines, what AMD had done in their sort of examples is they've generated a lot of very easy to access intermediate representation for all these different operations. So we just cheated there. We took that intermediate representation, we put it in a library, we put placeholders in for things like the problem sizes, things like the data types, and then from that, our compiler flow just fills in the blanks effectively and drives it through. For Tenstorrent, we actually don't do that. For Tenstorrent, again, there's lots of examples, but we actually construct the intermediate representation explicitly or directly, if you like, on a case-by-case basis within our compiler stack. So it's a matrix multiplication. Well, our compiler stack knows how to deal with that, and it just emits a whole bunch of operations through xDSL, through MLIR, in order to put this together. But it's sort of the same idea. What I've got is some Fortran code. I've got these intrinsics in it. I maybe have no idea that my machine even has a RISC-V accelerator plugged into it, but suddenly it just goes faster. And that's really the sort of thing we want to get to with all of this. Now, really the reason for doing this on the Tenstorrent architecture was as a sort of a way in or a step in, just in terms of getting our story right on the host and driving it on the host. And the reason I'm really saying that is because the AI engines, and actually the reason they're more interesting for this specific example, is they're tightly coupled with the CPU. You've got the same physical package with the cores, and then you've got the AI engines. Whereas with a RISC-V accelerator such as Tenstorrent, I've got to go over PCI Express, which, for this sort of use case is probably a little bit less interesting. But where I'm really excited for this, and I think we're going to pick this back up, is as things like Ascalon come out of Tenstorrent, it'll be fascinating to see if they combine that with any of their Tensix stuff, and actually if they do and have that close packaging, well, maybe potentially these sort of things will be very effective, because you've got this, again, this close coupling within a single memory space and just being able to dump things out and run these things. And actually, we're sort of already seeing this on the black hole cards with their application cores, and then the Tensix units around that, even though I'm not sure they're entirely designed for that sort of flow. But again, it's nice that they've got that possibility even on the black hole. As I say, this is fine, but actually what excites me a lot more is the general purpose side of things, and actually generalizing things like the Tenstorrent. As I say, Tenstorrent is an example. There's lots of other architectures out there that are RISC-V based that would also be good to enable for this. I think the key thing we need to be able to do or get to in the community is making this as easy as possible for the end programmer. Because whilst the Tenstorrent compiler stack is really cool and it's great, and some of us very much enjoy playing with it, it goes back to this point that the end scientific computing programmer is realistically not going to be spending lots of time rethinking their codes and then moving them over and completely changing them for the API. And one of the key challenges with this is it isn't just that changing it for the API, the sort of syntactic change, it's also that rethinking for actually what is quite a different architecture with different pros and cons to the CPU or even to the GPU. And this problem is going to get even more and more and more of an issue as we see more and more accelerators coming online based upon RISC-V in lots of different ways. And so I'm a firm believer that we need to be making it as easy as possible for the programmer and leveraging existing technologies. And so what we're focusing on here is driving this with OpenMP, because what I said earlier on is OpenMP is a technology that HPC programmers are very familiar with. They've used for many years around the threaded programming, but now they've been picking up and using around offloading to GPUs as well. But equally, there are other options like OpenACC, and again, hopefully we can get to a point where it doesn't matter too much. Again, it's this sort of common sort of intermediate way of representing things. But just to give you a quick view of this, this is a very simple Fortran loop. Target means offload it to a specific target. So here it would be a Tenstorrent thing, or it could be a GPU. And then teams will break up the threads, which is an OpenMP abstraction, into different teams and different numbers of teams, and then distributes the workload across this using both distribute and this parallel do as well. And the semantics of this are quite well known in terms of whether you get a subset of loop iterations per thread or per team, etc., etc. And also the programmer is able to specify their data. So here it says, what I want you to do is grab C from the accelerator once we finish this. And it's not specifying anything about A and B, these two things. So the default is just to copy them both on and both off. But also, it gives us quite a nice bit of flexibility around the way we do data between the accelerator and the hosts. And again, this is something that the HPC community is becoming more and more familiar with over the past few years. Very broadly speaking, I often think the bottom thing is the easiest, certainly from a compilation perspective, because it's a bit more static in terms of having this data region that we enter and we exit. This thing here, I think, is slightly more complicated to handle because it's more dynamic with having a data region and then being able to update things throughout the region. And really, when I'm talking about more complicated, I'm actually thinking about the intermediate representation that the compiler generates in terms of handling this. Because what becomes, again, a bit of a pain is when you, with the dynamic case, you don't quite know exactly what data is there absolutely 100% because there could be conditionals. So it has to be able to handle, if it's already there, we go with that, or if not, I go with an implicit approach. So there are a whole bunch of sort of edge cases in terms of handling this. So what we've done a whole bunch of work. Just to give you a simple example here, based upon this. So this is Fortran code, runs on the CPU. But imagine we've got a wormhole or black hole card plugged in to the machine. I probably don't know that much about the architecture, but as a programmer, I've got a very abstract sort of general view of the execution model. And what we've adopted here, and we actually might tweak these semantics a bit, but what we've adopted up until this point is the idea of, okay, you start with this, you then decorate this with target. So this will do the offload. And what this will do as sort of a default is this will take the loop and this will offload it to the accelerator. But actually, because you've not given me any more information, it will just pop the loop on one of these RISC-V data mover cores. So they call them one of these baby cores. So you can imagine at the top level, we've got lots and lots of these Tensix blocks. And this is one of these Tensix blocks. And then in here, we're executing this loop. Now, this is not going to go very fast, but this is sort of the default without any further information. And again, because I'm not providing any information about the data moving on or off, it will copy everything onto the accelerator, process it, and then copy everything off. And again, I might want to optimize that with the to and from, which OpenMP programmers are very familiar with. But then we can optimize this. So again, what we've sort of adopted here is this idea of the SIMD pragma, that's a part of the OpenMP standard, saying, okay, well, I am now guaranteeing that loop iterations are independent and they can be mapped to SIMD lanes. And here what we're calling SIMD lanes are actually different elements in my source register that go either into my matrix unit or my vector unit, and then come back out. So with this, actually now I'm no longer running iterations of the loop on here. I'm actually doing them as they should be done, which is on the coprocessor, which is down here. And this is now taking advantage of all the architecture in terms of getting data on, processing it, getting data off. And whether we use the vector unit, whether we use the matrix unit, really depends on what the operation is, and also options that the programmer can provide just the compilation pipeline for whatever reason. But the programmer's not really aware of this. They're aware of this very abstract model. They're also not aware of things like optimizations, such as, for instance, if I want to compute in the matrix unit, well, the result goes into dest. But when I go to the vector unit, well, it always comes from dest. So I don't need to go back out and back in. I can just keep stuff in there and just fire it straight through. Or the other way around, if I go with the vector unit and the matrix unit, I can copy from dest back out to the source and then fire it back around. And it sort of, again, I suppose another thing related to this is when you actually get into the details of what some of the API is doing here, it's not always obvious. So this is where we need to go in and say, okay, this is our initial API call to drive this, but maybe that's not the most efficient because it was designed for AI machine learning. This is more specific based upon the information we know. Well, actually, I'll drop down to the sort of assembly level and do this in a slightly different way than what Matillion does. But again, that will give us a bit more flexibility and helps us out there. And then lastly, obviously, that's just one Tenstorrent unit. We want to run on the entire accelerator. So this is an image of an architectural image of the wormhole from Tenstorrent's ISA documentation, and each of these are 10.6 compute cores. And what we're saying here with the parallel is to parallelize over these, and then using this num threads to say, okay, I want 10 of these, so I'll run on 10 of these different units. Now, as I say, where we are with this at the moment, I'm not entirely convinced that the mapping between OpenMP Pragma A and exactly what we're doing here is the most natural mapping. But really what this is enabling us to do is test and drive the compiler ecosystem written in MLIR behind the scenes. And then as we're getting more experience with this, sort of tightening up exactly what means what and how we're doing this mapping from the programmer's perspective. And just to talk about how we do this in the MLIR side of things, again, a lot of this is shared with what we'd already done that I talked about with the stencils, and what we've done with the intrinsics on the AIEs and the 10.6 architecture already, where we go from Fortran, we use this existing flow into the core dialects, including OpenMP, and then we actually lower down to another dialect we've got around devices, and just simplifying some of the OpenMP intermediate representation. As I say, it is designed to cover lots of different scenarios. So yeah, this just makes our life a bit easier. We separate them out, and stuff for the host, we've actually got a host dialect that we then feed through into function calls, and then with a runtime library, and then it just generates a host binary. And then for the device code, we go in and we figure out the dependencies between the operations and what depends on what, how these map to the Tenstorrent circular buffers. And then all of this gets split apart because we need separate kernels for the data movement and for the compute. And then as we're going down on the compute, we're doing this mapping to the different units and the optimization of this I briefly talked about. And on the data movement side, getting the data in, getting the data out, and communicating between these different parts of the 10.6 unit. And then what we do here is we've got printers generating C++, as I talked about with these APIs. And this is then effectively called by the host binary using their just-in-time compiler, which produces binaries and just launches it. But really the purpose of doing a lot of this is it comes back to this idea of the reuse. We're using as much as we can from previous work that we've done. So, just making those little bits for the architecture, but also trying to do this in a way where this can be reused as much as possible for other RISC-V architectures. Because lastly, if I zoom out, I suppose this is our master plan. I mean, I've talked heavily about Fortran. Actually, what the community is also doing a lot of work on at the moment is the new Clang front end for MLIR. This is really exciting. It's not quite mature enough yet to integrate, and it doesn't yet have OpenMP target offload. But when it does, our plan is to integrate that into the core dialects. And you can see lots of technologies here. Some are RISC-V, some less so. Blue is we've got a mapping which is mature, it's published. Red is we've got a mapping, it's either work in progress or we're waiting for the paper to be accepted, which is the case for some of this OpenMP stuff with the Tenstorrent side of things. And some of this is quite phenomenal. I know it's not RISC-V, but with Cerebras, for instance, with stencils, we've just had a paper accepted on this, and we can very convincingly outperform handwritten code by the vendor just by leveraging specific knowledge about the problem and the architecture and bringing it all together. And so what really excites me about this is really trying to move to the situation where MLIR is this building block, this middle block that gives us the reuse, gives us this ability to make it as easy as possible to bring these new accelerators online where we meet them in the middle. They've done a lot of work maybe on the enablement for the AI and machine learning. We as a community have done a lot of work thinking about HPC and the optimizations around there. And there's actually just a little gap in theory to connect in. And also, as I say, part of this story isn't just RISC-V, because there's lots of vendors out there like NVIDIA, like AMD, who are also investing heavily into the ecosystem that we can exploit, that we can benefit from with their investments, things like Flang, things like MLIR, that enable us to then progress forward and not have to rely on massive software teams, massive software efforts, just to be able to make these things available. So thank you very much for listening. I suppose my key point here is seeing lots of exciting hardware coming out with RISC-V. It's all for nothing as far as scientific computing is concerned. If we can't program it, we can't program it easily, and we must bring the hardware to the programmers. And there's some really exciting work going on in and around the community in doing this. And I think MLIR, LLVM, again, as a lot of us across the community probably already appreciate, is a key building block of this, and one of the great benefits of openness and the open way of working. So as I say, thanks very much for listening. If there's any questions, any discussion points, it's great to jump into them.
Thank you very much, Nick. So we have two questions here. One from the first one is, are there any instruction level accelerators that would really help transcendental function itself? So it's from AI Martin. Are there any instruction level accelerators that would really help?
Yeah, sorry, I'm struggling to understand the question purely because help what in terms of the performance, the adoption in HPC, addressing this programmer issue. I don't know, Al, if you can maybe just dump in the chat sort of specifics on that.
I think the person
I suppose
that left the chat left the event, but anyway, we can clarify it later.
Yeah, I mean, I suppose one thing I will say, and this probably doesn't answer the question, but a thought I've had, I talked about GPUs unifying the memory space, and that actually makes our life much easier with HPC, but we still have the challenge around a separate instruction space. I do wonder if things like the vectorization standard, things like the matrix extension standards, does this help us unify the instruction space as well? So this is a much more tightly coupled unit in terms of I've got my CPU, but it's just a really obvious extension to the CPU. That's my accelerator. And maybe actually that's a much more easily programmable, easily understandable thing as part of this. I'm sort of just throwing this out there. It's a thought I've had in the past in terms of it's not a completely mature thought. Actually, does this help sort of progresses towards this that maybe other technologies don't have the opportunity for? I see. Shall I just pick these off, Raphael? I see another
Yeah, go
one.
ahead.
Yeah, I see another one talking about if the MLIR approach is compatible with CUDA. The answer is yes. I mean, in terms of if you go down through the MLIR approach, you enter NVIDIA's own bit of that, which generates PTX out of it. So it's sort of what CUDA would integrate with, and actually a lot of the MLIR NVIDIA GPU dialect really, feels very familiar to CUDA for me. So one thing I didn't show, but was in the ASP+ paper that I linked to in the presentation, is we get really good performance actually with stencils through that flow, compared with just generating CUDA and generating other things like OpenACC as well, just because some of the optimizations we can do a bit higher level up on the stack. So yeah, I think my personal feeling is it's quite well integrated. It would be very interesting to hear from a NVIDIA engineer from their perspective how well integrated it is. Because obviously what we don't always get to see is how good that PTX is, because it's sort of a binary blob that comes out. But what's really exciting is when NVIDIA brings CUDA over to RISC-V, potentially that's all existing, that's all there, and it might just all work. So watch this space for 2026. Leonardus has said, if I understand well, when we parse Fortran OpenMP, find generate some API calls that are responsible for memory transfers and offload. So we just need appropriate facilities in the accelerator. Great question. It's actually quite a lot more involved than this, and it's more involved for two reasons. I mean, you're absolutely right. There are some API calls, but there's also a lot of OpenMP specific intermediate representation in the OpenMP dialects. So this is things like representing loops. This is things like, the SIMD, pragma, reductions, a whole bunch of things in the intermediate representation. And that's important because it's guaranteeing certain semantics or certain limitations around loops and the fact that iterations are independent. Now, for threaded programming, of course, what happens ultimately is that becomes API calls calling into something like pthreads or whatnot. What's a bit more complicated for accelerators, whether it's GPUs to some extent, but certainly for these other accelerators, is closing that semantic gap, because things like the Tenstorrent accelerator, the execution model is really quite different from what somebody might have on the CPU with threaded programming or even on the GPU. And actually, what's a thread? What's a SIMD lane? So it's that mapping from one to the other. So where we do quite a bit of work is taking that OpenMP intermediate representation and being able to follow that through for things like understanding the dependency of operations, mapping to the most appropriate bits of the architecture, but also separating out onto these different RISC-V cores, getting data in, getting results out, driving the compute unit as well. So yes, it ultimately ends up in the API calls, but that intermediate representation of OpenMP dialect is really important to be able to extract this information and, as I say, specialize it for the architecture. And for us, that's the really interesting thing as well. And I guess, sorry, just one last point on that specific thing. What fascinates me is this idea, when we bring in new RISC-V architectures, can we generalize some of that specialization? How much of that is generalizable? How much of that needs to be on an architecture by architecture basis? And then the relaxed memory consistency guarantees are handled in the intermediate representation. So tell me if I'm misinterpreting the question here, but yes, certainly what we do is we exploit the what OpenMP is guaranteeing or what it's not guaranteeing, and we take that as gospel truth, if you like, to then drive that for the architecture. And there's certain things and certain restrictions we have to place on this in terms of being able to communicate between threads, but then certain benefits in terms of guaranteeing things are independent, and whatnot. Where it becomes maybe slightly more complicated is things like flushing memory and guaranteeing that. But there's sort of ways of doing that often with the API and just making sure that conforms with, again, what the programmer expects based upon the standard and what's in their intermediate representation. And sorry, the last thing I'll say on that is sometimes we can cheat. Sometimes we can say, and it's actually not what we're doing with Tenstorrent architectures, but we might say, well, we're not going to support this specific pragma because we can't provide that on the accelerator just based on what they provided. We'll do this other thing that's maybe a little bit weaker or has more constraints, but actually it's easier to support, or it's possible to support, and we can do that.
Right, I believe we do not have any more questions. So if you want to get in touch and get involved, so you are more than invited to join the HPC that Nick leads. So I believe that they're not sure if they have more meetings this year, but if so,
yes, we've got one in December. This is the third Thursday of every month. And what I would also say is on the link at the bottom of this slide, xDSL project on GitHub, a lot of what I've talked about is up there open source. The little bits that aren't yet will be open source as soon as the paper gets accepted. So that's so there's a lot up there already, and then there's the stuff that will go up in January as just as the paper gets accepted. So please take a look at that. If there's anything you've got question-wise, just reach out. More than happy to chat. And I'm happy to make the slides available for Fabrizio. I can send them to Raphael if that works.
I can attach that to send me the slides and attach to the final environment where we're going to publish this. So thank you everyone for joining. This presentation is recorded. We're going to publish that at our RISC-V YouTube channel between today and tomorrow. Again, if you need more information, get involved, join the HPC. And Nick, thank you very much for presenting. Thank you for sharing. And we are more than welcome to come back to another RISC-V technical session and present again about how things are evolving.
Cool. Thank you.
Thank you very much. Thank you. Bye-bye.